Hi again. Today I'll show how each one of you can simulate a satellite revolving around the Earth using your own personal computer free of cost. Yes, each one of you free of cost can simulate a satellite revolving around the Earth, and with the help of which will realize that the phenomenon of a revolving satellite is essentially similar uh, to a pencil falling off the table, or for that matter anything falling towards the earth when you release that object. Okay, so here's the thing. There's a website called Wolfram Cloud, which anybody can go to and make their free account. Okay, so I've made my account, and you get a basic free plan, but with that plan you can do quite a bit. So once you have registered using your email ID and password, you get to see this your home page in wolframcloud.com. So you can open a new notebook. So that's your pristine new notebook, and in this notebook you will write up some code. So to save time, I have already prepared the notebook. This is our code, and a few comments. Anything inside parentheses star, like for example this one, parentheses star from the left and from the right, is basically a comment which the computer will ignore. Same applies to all of these texts, right? All of this is comment. Okay, so you can copy this code as I have written over here. You can copy this, and if it's too much, if you can't copy it manually, I'll show an easy way to copy it towards the end of the video. Okay, so I have this code, and all you have to understand, or take care of, is that this parameter R0 is the initial distance of the satellite from the center of the earth in meters. So this number is in kilometers, and I multiply this by 10 to the power 3 to convert this to meters. This is the initial speed of the satellite, not in meters per second, but rather in kilometers per hour. That's what you can enter. And this is the air drag factor, meaning if you want the air resistance to play a role, you increase this number. And this is the final time. Tfin is the final time. Till what time? Starting from t equals 0 seconds, till what time do you want this simulation to run? So these are the only 4 parameters that you can that you have to touch. You don't need to worry about what's written over here. You just have to copy all of it, and you can tweak with these first 4 parameters, and I've explained the meanings of those parameters to you. Okay, so how do you run it? So the way to run is that you go to evaluation, and you can click evaluate all cells, or I can just be here with the cursor blinking inside this cell. It starts from here, it ends here, and I can hit shift plus enter. So when I do that, the picture is refreshed and the code has run. So that's how it works. Okay, so let's see what this simulation is telling us. So first of all, I have this blue circle is the earth, and the red trajectory is the trajectory of the satellite, or the object that has been released from the sky. So the object is always shot horizontally. From this point, it's shot horizontally from the earth in the sky. So let me start with a small velocity, like 19,000 kilometers per hour is a very high speed. Let me start with, let's say, 190 kilometers per hour. I press shift plus enter, and you can see what happens is that the object starts from here and it crashes on earth. This blue line is the earth, and I'm zooming it in, like zooming in very deeply. So that's why you see that the earth appears as a flat surface. But from a global point of view, this is what is happening. This is the earth, and this thing is released, and it falls some distance away from its initial horizontal position. Like, it's a very small distance, because the speed is very small. For now, let's just let's ignore the air drag. We'll set the air drag to be 0, meaning we'll assume there is no air. It's just earth and the other object. So we'll run it again and it's similar, right? So this is basically, this is like an object falling on the surface of Earth, which is pretty much understandable to us, right? That's how an object falls. You release it, it falls towards the Earth. Now let me increase the speed a bit. I'll increase it to 10 times the previous speed, 1900 kilometers per hour. And with that, I hit Shift plus Enter and it is again run. So you can see that now you have started to realize, to see the curvature of the Earth. You see it's not totally flat, it's kind of, it appears slanted because this time the object travels much farther. It goes up to like 800,000 meters away from its original horizontal position, right? Earlier, at the earlier speed, like at 190 kilometers per hour, it went up to only like 80,000 meters away. But this time, with 10 times the speed, it has gone up to, you can see, 800,000. And even from a global point of view, from this vantage point, you can see that yes, it has traveled much farther. So yes, it's again very similar to a coin being flicked off the table. A coin just, it keeps on traveling and it falls towards the Earth. It's the same kind of trajectory. But as we increase the speed at which we launch, something interesting starts to appear. To you, it might seem that, a school student or a physics layman might see an object falling on the Earth like a pencil or a coin, very different from a satellite revolving around the Earth, but they are essentially the same. And we start to see that if we increase the speed even further. So instead of 1900 kilometers per hour, let me launch this with a speed of, let's say, 7,000 kilometers per hour. What happens? Okay, and here it travels much farther. That's fine. That does not show us anything interesting. Let me go to 12,000 kilometers per hour. And now we see the same phenomenon. It's traveling farther and farther away. Maybe I'll need to go to, let's say, 18,000. Does anything interesting show up? Oh yes, look at that. So to understand that, let me decrease the speed further. Let's say 15,000. It's still, so now you can see that with 15,000 kilometers per hour, with that initial speed of launch, it is able to cover about a quarter of the Earth's circumference. It's gone around the Earth only like a quarter of the journey, right? Now it seems plausible at this point, if I were to increase the initial speed launch, it might go further and further around, right? And that's the characteristic of a satellite, that they complete full journey around the Earth. So with that hope, I'll increase it gradually because this is the point where interesting stuff happens. So yeah, look, it's going around further and further. 16,000. Let's go to 17,000 kilometers per hour. And look even further. So let me make it 17,500. Gives us, wow, look at that. That is it. It kind of, so there comes a point when it kind of totally misses the Earth, right? So at 17,000, it did not miss the Earth. It did strike the Earth here, right? But if I were to increase it further, you can imagine that this might very narrowly miss the Earth, and if it misses, it's going to join up again. And that's exactly what happens at 17,500. So yes, it misses the Earth, and what happens then? It joins again back where it started from. And you know what? It comes here and it keeps on going along the charted territory. It keeps on tracing its own path, and hence we call it a satellite. So basically, the difference between an object falling straight on the Earth versus a satellite, it's just a matter of speed in this crude, rough simulation, right? That's it. That's quite interesting. And if I increase the speed even further, let's say 20,000 kilometers per hour, it kind of becomes a bit different, but it's still a closed circle. So you can see that this object is revolving around the Earth on and on, again and again. Okay, that's quite interesting. Now let me turn the air drag on. This is all assuming there is no air, so it keeps on revolving. But as you can see, when an object goes through air or water, they tend to lose energy because of heating, because of friction, because of rubbing against the air or water molecules. So it seems plausible that the satellite will lose energy and will spiral towards the Earth, right? And fall on the Earth eventually. So let me increase the air drag to, let's say, 20 units. And I run it again, and that's quite interesting. Look at that. So it is spiraling as we anticipated. It doesn't spiral towards the Earth, becoming, coming closer and closer, and finally at this point here it really smashes into the Earth and the simulation stops. To see it more clearly, let me increase the air drag to even higher numbers like 35, and it becomes even clearer, or let's say 45 probably. Yeah, you can see it starts from here, comes closer and closer, and at this point finally its journey ends because it's dragged towards the Earth. There is air. Air doesn't let the satellite keep its original energy, so it loses energy and comes close to Earth and gets smashed. Okay, so that was it. It's a nice, nifty simulation which shows the universality of physics. Newton's laws of gravitation can explain a simple object, an everyday object falling on the ground, as well as a satellite, a celestial body like a moon going around the Earth, or a satellite going around the Earth. It's the same. The differential equations, the laws of physics, they are exactly the same, which have been coded here. But you don't need to understand them. But that's the basic message: universality of physics equations. Okay, now this is fine. You can manually copy all this code and on your free Wolfram Cloud account. And if you don't want to, I have made this GitHub account for you all. github.com/with satellite simulation. It's available to everybody. It's a public code, and there is a .nb Mathematica notebook file. So if you have Mathematica on your computer, you can simply download this .nb file and run it on your computer. It looks like so. Just a moment. Okay, I think I've lost it. But yeah, you can simply download and run it. And there is a PDF version too. You can click on this PDF, and here is a PDF version of the code. This code which I wrote here. Maybe there are few changes, but nothing substantial. So you can copy and paste this code. You can download it on your computer and copy and paste this code in your Wolfram Cloud account. So yeah, try this code out, make some changes, and let me know in comments what do you think. What other interesting features or phenomena could you uncover using this code? Okay, so I'll see you all next time. Take care. So during the main video, I could not show you how to open this .nb file, the Mathematica notebook file. So this is how it looks if you were to download that .nb file. It's basically a Mathematica notebook, and the same code is coded over here. So all I have to do is just like before, shift enter, and these two plots are generated. So yes, you can use this .nb file if you have Mathematica on your computer, which is it's a proprietary software. You have to pay for it. Only then you can run it the way I'm running it over here. But that's okay, even if you don't have it. This Wolfram Cloud is free of cost, at least the basic account, and you can get this code either from this video, or you can just go to this PDF, satellite simulation.pdf, to get the code. Okay, see you next time. Take care.